Welcome to Future Fairs. Good evening, ladies and gentlemen, boys and girls. Today we embark on an intriguing exploration into world of PCI coal combustion and its intricate dance with alkali in the blast furnace. As chemical reaction unfold, the influence of high sodium content become paramount. Let's unravel the secrets within. As PCI coal undergoes combustion, crucial sodium compound such as sodium carbonate and sodium sulfate comes into play. Their low melting points lead to formation of molten droplets, resulting in the creation of slag that deposit on cooler surfaces. These as depositions significantly affect heat transfer within the blast furnace. The accompanying blast furnace image serves an illustration tool offering a general depiction of all reactions and the coke damaging zone in blast furnace environment. It is important to note that the specific intricacies of alkali impact on combustion and coal ash deposition are subject to various factors, including temperatures, coal composition, and furnace condition. The image is source for visual representation and doesn't replace in-depth analysis. Our consultation with relevant studies on alkali interaction in industrial processes. Now let's spotlight the role of sodium in car combustion. Sodium act as a catalyst. Sodium lowers activation energy, allowing car to burn at lower temperatures and faster rate. The result enhance combustion efficiency and increase heat release, vital for energy demands of the blast furnace. Moving on to our next key aspect, the combustion of car. Now, car is the solid residue that remains after the volatile matter in coal is released during combustion. Now, what's fascinating is the role of high sodium content in this process. It acts as a catalyst, a sort of facilitator, lowering the activation energy required for reactions, particularly the oxidation of car. This reduction in activation energy means that car can now burn at a lower temperature and a faster rate. The practical result, increased combustion efficiency. What's more, this enhanced efficiency leads to a higher consumption of car during the combustion process, resulting in elevated combustion rate and potentially increased heat release. So, in simple terms, the high sodium content is not just a bystander in combustion, it actively accelerates and optimizes in our ongoing discussion. Now let's delve into practical example to illustrate the real world impact of sodium content on combustion. Consider two coal samples, coal A with low sodium content and coal B with high sodium content. During combustion of coal, the process proceeds at a normal rate and as deposition remains relatively low. Why? Because there is a lack of significant molten sodium compounds. Now shift our focus to coal B. Here the high sodium content leads to formation of molten sodium compounds during combustion. These compounds deposit in cooler surfaces causing a noticeable increase in ash deposition. But that's not all. These sodium compounds also act as a catalyst promoting a faster and more efficient combustion of car. Now let's talk about the allowable alkali loads for key materials in blast furnace. And this is also going to very important aspects in our daily operation of the furnace. Iron ore less than 0.2 of the ore weight, coke typically less than 0.05% to 0.1% of the coke weight. PCI coal, which is supposed to be very important, generally less than 0.03% to 0.04% of coal weight. And limestone generally less than 0.2% to 0.3% of the limestone weight, and dolo simply 0.3%. These strict limits highlights the need for precise alkali management, crucial for maintaining furnace efficiency. As we delve deeper, we will explore how these limits shape the blast furnace dynamics. Now we are coming to the impact on hot metal quality. As we can now let's shift our focus to the crucial aspect of alkali removal in the blast furnace. Once the combustion process is underway, approximately 10% to 20% of the alkali doesn't contribute to the intended reaction. Instead, it needs to be carefully managed to prevent undesired effects. This surplus alkali is efficiently removed through the top gas as the gases from the furnace flow through the dust catcher. A strategic component in the process, alkali is captured in form of dust particle. These particles are then meticulously separated from the gas stream before it is released into atmosphere. These meticulous removal processes ensure that the blast furnace operates with controlled level of alkali, preventing potential environmental and operational challenges. As we continue, we will explore how this systematic approach contribute to maintaining the delicate balance within the blast furnace environment. Now let's turn our attention to the crucial factor of alkalis in the hot metal produced by blast furnace. The acceptable level of alkali in hot metal is typically maintained at less than 0.06% to 0.07% of the weight of metal. Regardless of how the alkali is transferred, it's widely acknowledged that the alkali metal in coal can exert a negative impact on the tendency to react with iron, forming undesirable compounds such as potassium iron sulfide and sodium iron sulfide. These compounds can significantly reduce the ductility and toughness of iron. Furthermore, alkali metals can also encourage the formation of undesirable phases like pearlite and cementite. Further compromising the quality of iron produced, it is essential to note that even a modest 0.1% increase in alkali content of feed material has been reported to correspond to a noteworthy 1% decrease in hot metal production. To put it into perspective, the impact is tangible. 0.1% alkali can result in additional 6 kg per ton hot metal coke consumption. This underlies the critical role of alkali management, not just in maintaining quality but also in ensuring optimal efficiency in the production processes. As we delve deeper, we'll explore the nuances of mitigating these challenges in the pursuit of high quality hot metal.